In the name of Allah, thank you so much. Welcome back to the lecture number 8 of the intelligent sensing and remote sensing. So this is almost the second last lecture. So this lecture is about, as per the glance perspective, it is the advanced analysis and its application. So this lecture is specifically spectral transforms. We are dividing the spectral transform into multiple types, linear and non-linear. We will discussing again more principal components, transforms in more detail. In the last lecture, we have already discussed the principal component, but here we'll be transforming them more in depth. And we will also discuss a couple of the analysis methods of the non-linear, linear transforms. So this is the second last lecture. Let's jump to start. Starting with the vector space. In multispectral, as this is the spectral transform, so we should have to know about them. So far, we discussed multiple times multispectral and hyperspectral. So multispectral remote sensing, each band can be considered as a one dimension. So we have multiple bands. So each band is representing a single dimension. For example, if an image has a 6 bands, um, each pixel can be represented as a point in a 6 dimension spectral space. So we can say this is 6 dimensional spectral space, this image. So each dimension has a physical meaning because each dimension correspond to a sensor band. That is obvious that each dimension has a physical meaning because it's directly associated with the instrument. So from the instrument, we mean the sensor, and each dimension corresponds directly to the hardware or sensor. That's why here we are discussing the vector space. So it's not anymore a single value. So it is a transform in the space form and in a vector form. So the core idea is a multispectral pixels is not just a one value. It is a vector of band value. So in a vector, we can have a multiple values. As we know from the vector, they are having the direction and space, everything. But we are not moving in the mathematical aspect and we understanding the concepts of the advanced analysis. So it's less mathematically. So examples is like pixels for blue bands, green, red, near infrared, short wave, infrared 1 or 2. So all of these are becoming a single vector, and this vector represents the values for each respective band. On the right side, you can also see this is the 1 pixel equals to 1 point. So blue band and the green band, they are representing the near infrared. So it is becoming a single dimension, a single vector for multiple band values. So that's why we call them the vector space. Spectral transforms. So we are now having the spectrals of multiple objects from the bounce back electromagnetic waves. And its spectral transfer response depends upon the material and its thermal or emissivity. We already discussed these things. The idea of the spectral in the advanced analysis transform is to we extract the features. So the spectral transform convert the original spectral space into a new feature space. That is the core idea of this one spectral transform, meaning we are now having the sense transform and the sense spectral, which is after certain pre-processing of the uh, data correction in basic analysis. So far we have seen, but we would like to transform them more. In the idea of the more transformation is to extract some more features. The original spectral space is based on a one physical sensor based, and each band correspond to its wavelength. We already know that the bands have been taken in multiple wavelengths, but the feature space, after transforming the spectral response, which we have observed or sensed using the sensor, it is in the original spectral space. It is the physical sensor band, and then it is taken by multiple or correspond to multiple wavelengths. The feature space is created by mathematical transformation. This is the mathematical transformation of the physical bands. It is designed to highlight the useful information in the certain the spectral response or reflectance. It is designed to highlight useful information, may reduce redundancy. The main idea is redundancy. We have a similar information. It may make classification more easier because in classification, we will discuss in the next lecture the land cover classification, and it's more like AI method. If the spectral response is like more feature based or feature based, the classification is really easy to assign the classes, and the machine learning will be really easy identifying them. In the core idea is the spectral transform creates new bands features from the original bands to make information easier to extract. This is the whole idea that we are exactly preparing the data for classification, AI, and more advanced analysis. So the spectral transforms or creates new bands or features. If you see the word bands, the bands is exactly using for the original space, original spectral space or the original spectral response bands. But when it transforms, so the idea like mathematically transformation applied, so it is not anymore the original spectral space, it is a features from the original bands to make information easier to extract. So we are making this information to further be classified and assigned on the mathematic style. Linear in nonlinear transformation. This is the exact idea we are looking for. So we have discussed what is vector space, then what is spectral transforms, and now this is the main differentiation of between or two types of transformations we have. It's a linear and nonlinear. Linear transformation is a or linear combination of the original bands, like spectral transform is exactly one of the example. We have already seen this principal component, but here we are looking into the principal component transforms, or it's more or less the same, but here we are only a little bit looking in more detail in a new method of the transformation. It is doesn't care. A nonlinear transforms is like new features are produced using nonlinear relationship between the bands. So in this case, there is no directly linear relationship between the bands, but we are using the multiple bands as a ratio like NDVI, NDVI, in MNDVI and band ratios. So NDVI is nothing but it's normalized difference vegetation index. So this is specifically using for the vegetation as a ratio. NDVI is the normalized difference build up area index, and the MNDVI is the modified normalized difference of water index, and the largest band is band ratios. So there are multiple. For example, I have taken these three as an example in this lecture. The simplistic idea is a linear transforms mix bands using the weights. The linear transforms mix bands using the weights. This is the overall idea. Like the linear transform is using as a weights for mixed bands using weights. Non-linear transform usually use ratios or normalized differences. So this is normalized differences they are using in the non-linear transformation. In the linear, we are using the mixed bands using its weights. If you see as an example of the principal component analysis in the linear transform, so we are having multiple bands, but we are taking the top most principal components as a more having more information. The later on principal components having less information, but still it's valuable. If you would like to remove the noise or remove the important information, so the remaining will be the noise. So still you would like to keep those principal components also. And this is how we are using the next bands using weights. But in the nonlinear transformations, usually uses the ratios of the red bands and blue bands and green bands, so which is representing a different stuff. So we will be looking more into these each step by step. And the right side, we can also see like again some of the quick explanations. So we will see the initially linear transforms. In the linear transforms, we are discussing why principal components transform is needed. First of all, that's an important question. Already discussed that the multispectral bands, so we will go quick in these. Already covered some of the basics and foundations. So when there is certain information which is highly related, so we will focus on that more. So multispectral bands are often highly correlated because it's having a multi-bands and it's more narrow to each other and the wavelength. So this means several bands may have a carry similar information. And the reasons for the correction include is like spectral continuity, like spatial continuity. Have we seen the properties of the next nearby pixel value is more relevant. So that's why spatial continuity is important. So here is the spectral continuity. The factors usually change smoothly with the wavelength. Sudden changes are rare. It is just due to the continuous collections. So neighboring bands often looks that's obvious, like the same example of spatial continuity. In topography shading, let's suppose if a mountain shadows the effects in the area, it is usually affects many reflected bands at the same time. So all of the bands will be having a similar kinds of information, and from all of them, maybe one or two bands required. Otherwise, should we need to skip them or ignore them? Sensor-based overlap, neighboring sensors bands are designed to be separate, but their wavelength response may overlap. So from the neighboring sensor exactly mean like a different acquisition can be overlapping or the other satellite which captures maybe the same area. So there is an overlapping chances. So neighboring sensors bands are designed to be separate by chance. If it is a single satellite, we have multiple. It is designed to be separate, but their wavelength response may overlap. Like two neighboring sensors can capture the same, so there is a chances to be overlap with each other, certain wavelengths. So they can be measured partially or similar information. This is very high due to all of these reasons of sensor-based overlap, the topographic shading, and the spatial continuity. Although these things were not most in detail explained in the previous um, lecture of the basic analysis, but here it's in more depth. Core problems analyzing all the bands can be inefficiently because many bands may contain the redundant information. That is the overall idea. And the side needs a graph of the which they are showing the spectral continuity, topographic shading, and the bands overlapping. Now here we are going towards the need is exact, so we need to study the principal component transform. The principal component transform or PCT is a linear transform designed to remove the redundancy between the spectral bands, and it creates a new bands called principal component, and these components are uncorrelated. As we discussed previously, after the covariance matrix, we know in the off diagonal we are having a variance bands in the no in the diagonal we are having the variance bands, in the off diagonal we are having uh, covariance bands. I mean they have a subvariance with each other. So the ordered by information content and designed to concentrate variance information and is useful for dimensional reduction. That is the main idea. PCT transforms correlated original bits into the uncorrelated principal components. That's the main idea of they are trying to uncorrelate the bands. It is exactly useful for the information to be uniquely identified for the other bands. Principal components. This is the more details. In principal components are not original physical bands. We already discussed they are mathematically bands are created from the combination of the original bands. For example, the original data set has a 6 bands, so its PCT will start from the principal component 1 to the 6. So what the PC1 contains largest amount of variance or information because it's the more high difference between the other component. and it often represents the dominating brightness or main common patterns in the image. So the PC2 will contain the next largest independent information. It often highlights differences not captured in the PC1. So they are exactly a difference of the principal component one. In the latter pieces or principal components, higher ordered PC contains less variance. Higher mean in terms of as we are increasing the components, principal components, so they contain the less variance in terms of the information, so more or less relevant, but with a minor difference. So they may contain the small details, as I already said, the subtle anomalies in noise, minor class differences. So the important warning is that the later principal components may look noisy. Why? Because they hold some other kind of information, but sometimes they contain small but important information, especially in multi-temporal analysis. That is important. So this is a really useful. That's why we are keeping in multi-temporal analysis because these minor details can help us to, if we remove that from the complete set of information, so it is remaining is noisy, but we can capture the important information. So in simple terms, more variance, more information, and the later components, principal components, and less variance. As I said, in this, we are discussing this chapter more in detail about the principal components as compared to the previous one. So here is eigenvalues and eigenvalue vectors coming into the picture, which are the mathematically concepts. But here we are not looking into more mathematically in understanding these concepts and conceptually, like what is eigenvalues in terms of remote sensing and eigenvectors. So eigenvalues tells how much variance or information each principal component contains. So this is the main thing we are looking into, the each component variance of our data. The large eigenvalue, more information, or small, less information are probably the nice. Eigenvectors is define how original bands are combined. So this is eigenvector is looking because we have discussed that we have eigenvector space and we can have a single image with multiple bands. So that's exactly represented by the eigenvector. So eigenvector defines how original bands are combined to create each pixel, each principal component. So the main role of the eigenvector is because of the eigenvector space and can have a single image with multiple bands, so it can be represented better in my eigenvector. So that's why eigenspace. So that's why eigenvector is dealing with the band's composition and how it's created, like how the original bands are combined to create a new component. They are like weights showing how much each original band contributes to the principal components. So the eigenvector is acting like a weight. They are deciding how much information can contribute to a component. But eigenvalue is looking or checking into the exact information a single component is holding. So in simpler explanation, eigenvalues tell the importance of the principal component of a single component, but the eigenvector tell how each principal component is built from the original band. This is the main differentiation between both of them. Uh, Information conservation in principal component, this is really important. Principal component transform does not destroy the total information. As we know that in the principal component analysis, we are collecting the information from the original band. So how do they conserve the information? It is obvious that they do not destroy the whole information. It redistribute the total variance across new components. So in multiple, let's suppose in 2 or 3 bands, we can have a minor difference of data. So they redistributing the total variance of a data across the new components. Or let's suppose the 2 bands are becoming a single component. So they are trying to distribute the total variance across the component. Most information is moving to the first few principal components. As we said, the later or the higher components are the less information or maybe noise. This means the principal components contains most information, but PC2 contains less information. So later PCs contains progressively less. But the core idea, principal component correctness in correct concentrates information into fewer components, making data analysis more efficient. That is the core idea that they are trying to get the fewer component. And the reason of behind this is in simple terms, in the ultra spectral, the hyperspectral, if we see we are having hundreds of bands from 10 to 100, in with a narrow micrometer difference of the bands. If we are looking to into each band, it is useless and it can hold redundant or similar information. So the principal component concentrates the information into the less or the fewer components because it make analysis more efficient. And the reason why they are making an information or analysis more efficient because each component is a unique or uncorrelated. The information is new. So dealing a new information is better than the redundant. It will waste computation and storage. Information content of the principal components. After the principal component transforms, higher order components may be suppressed to reduce the dimensionality. And the reason is why there is no major difference between the bands. So this can be useful because fewer bands are easier to process. Exactly, that is the main idea. And redundancy is reduced, noise may be removed, the classification maybe become simpler because information is more already in the classes form or already pre-processed. But it must then be carefully because small component may contain meaningful anomalies. This is really important aspect it's point out here. If we look into the information of the higher components, as we discussed, they are holding less information, but keeping the bands or choosing the bands in a less components and or fewer components, fewer component from principal components. The reason is it should be done very carefully because there is a chances we can lose information, which will be really definitely a really small, but it is really meaningful information at the same time. So if we lose them in terms of the reductions of the bands to transform into the principal components, maybe lose information. So that's why it's really important say the information is meaningful, meaningful for the anomalies, and that's why it should be done very careful. An example, a small length cover change may appear in a higher order components. How this is possible exactly, this is due to we should have to be very take care in the procedure of becoming the fewer components and due to the meaningful information in the higher components we are putting, even if its variance is low. This is one of the main information like we are saying a small lid cover car change may appear in the higher order components. In the higher order components, while they are looking, although even its variance is low. So if we assume it's not important and we can remove it, so although we are losing the information. So this should be decided very careful and the higher component doesn't mean it's irrelevant. It is relevant, but for minor details or removing the noise, finding the good information from that. But one thing, if we say, you can say the limitation of the time series of the principal component analysis or PCT, principal component transform, that is the data dependence. By the data dependence mean the principal component is dependent on a data on a certain of images. Like this means the transformation depends on the specific images being analyzed in a certain time. The time is really important to be taken into note or time series. Therefore, the principal component from a different images may not be directly comparable. That is really important. And why it's not comparable? Because it's totally unique information. In the principal one in one image may not represent the same type of information as PC1 in another image. And the reason is why, because the total informations are different. And if we include the temporal info analysis or taken the pictures or acquisition at different times, so it is really difficult to understand or differentiate this thing or compare the principal component analysis. If image contains similar length cover classes and proportions, this is one of the cases that we can compare that if there is the land cover classes and proportions, their pieces may look similar in this case. So this is a little bit chances. Um, in the time series analysis, it's obvious that the new data will be captured in different location. So principal components are powerful, but their interpretation changes from scenes to scene. That is obvious. So regarding the class information, if the images contain similar length cover classes and proportion, their pieces may look similar. In this case, it is somehow comparable, but even it's still not effective. Could be changed due to the temporal analysis if we include that. So the correlated data is now going to uncorrelated data. That is the main concept of the principal component analysis. And that's why this is PCT is data dependent, and you can consider as a limitation of the PCT. Maximum noise fraction. Okay, signal versus noise. So we are comparing the maximum noise fraction or MNF is related to principal component analysis or PCT, but focuses more on separating a useful signal from the noise. That is obvious in the later or the higher principal components. We can see uh, lower details and still keeping them. And that's what we are trying to separate the useful signal from the noise. We know in the higher components, the encoder we also noise because the details are small, but still we would like to keep in the maximum noise per fraction. We are doing exactly the same, and the instrument noise is often uncorrelated because it's almost negligible, so it tends to accumulate in a higher ordered bands. It will be automatically finished in the higher order components, ordered bands. So even if tries to order transform bands according to the image quality and noise content. That is the main idea of the maximum noise fraction. So in the maximum noise fraction, we are keeping in the first those components which is a less noise. Then again, the second one, third, fourth, fifth, seventh, it's where we are going onward. And it is not only keeping or trying to the transform bands according to the image quality in noise content. They are looking to both. How much is the spectral response or resolution, spatial, not spatial, spectral response in looking into the noise, about how much noise the certain band they have. So according that the MNF or the maximum noise fraction is trying to set the components. In the code area, PC orders components by variance. Or variance is exactly the same, quality, content, noise content, and all these things. While MNF is designed to help separate signal from the noise. That is the obvious job of this the MNF we discussed as from the name, it's looking maximum noise fraction. So the ultimate meaning is minimizing the noise. But we have seen that the PCA orders component by variance. So variance is definitely by the data, how much event information they have. But here in the components, what is the role of MNF, maximum noise fraction? They are designed to minimize or separate the signal from the noise. Which noise? It is not the instrument or the sensor noise because we said it's uncorrelated here, and so it tends to accumulate in the higher order bits automatically. The idea is in the higher order components, there's still noise and they would like try to reduce that noise from the signals. This is the main idea of the MNF. We are having in the linear transformation or transforms another one operation or analysis tool. You can call them Tassel Cape. So the Tassel Cape transforms or TCT is a standardized linear spectral transform. As we are discussing spectral transform, so is more relevant all these analysis to the spectral analysis. Unlike PC, it is recalculated for every scene. This is a standardized spectral transform, not like a PCA or PCT, like recalculated for every scene. Why we are calculating? Because we see this is data dependent. For the temporal data, we can have a multiple images, so we need to calculate them again for new acquisition. So the mean tessel component includes brightness. In the right side is also shown brightness, greenness, yellowness, non-such. So this is fixed coefficients and sensor data dependent, but PCA is data dependent. This is sensor dependent. So what are the main components include in tassel cape? The brightness is overall soil or the background brightness. In the greenness is the healthy vegetation signal. Yellowness is the showing the descent or the dry vegetation direction, and the non-such is the residual variance. So the core idea is that TCT or tassel cave transform is a fixed sensor-dependent transform designed to produce interpretable features such as brightness and greenness. So it is mainly directly tassel cave transform with the sensor. So it depends upon that and the limitation or in the comparison. We will see this as an example or as a main feature that one of them is data dependent and the other is the sensor dependent. So PCA versus tassel cape or transform PCA and PCT. Transform the above one is PCA or PCT differentiation, and to the below one is the tassel cape. So the below one is the transform type in the tassel cape transform. Both of them are the linear transforms. In the coefficients, a PCA is data dependent, in coefficient is fixed or it's sensor dependent. So in the sensor, we can fix all these brightness, yellowness, greenness, and non-such mean residual. We have discussed this in the previous slide. It's the residual variance. So all of these can be fixed by sensor. So that's why it's fixed for sensors. And the main purpose is they remove the redundancy and concentrate information in PCA or PCT. But the main purpose in the tassel cape, it is to produce interpretable vegetation or soil features. That is the idea, to have some interpretable information about the vegetation, soil, and features. What are the comparability? Like if we go to temporal analysis or time series analysis in the PCT, they see it is hard across the different scenes because it is changing image to image. The principal component analysis, it can be calculated them. But the comparability in the tassel cape, it is more comparable for the same sensor because it's fixed. So fixed thing can be really easy compared with the other one. So because the same sensor is capturing the same multiple acquisitions with a certain fixed thing. But in that case, if you change the scene, it's totally data dependent and can be regenerating or recalculating a total different kinds of principal components. And as it is uncorrelated, so it's really difficult to compare them. The output meaning is more stable meaning in the case of the tussle cave, but in the output meaning changes by the image. So it is according to the image they are capturing. The sample explanation is PC is adopted in optimal for the specific image. It is adopted and it is a specific to an image dependent, you can say. But the tussle cave is standardized and it is easier to interpret. In the tussle case, it is easier because these are the certain fixed things like a brightness, greenness, and yellowness. Each respectively represent different information. As we have seen in the previous slide, the brightness is representing the overall soil or the background features. Brightness or the greenness is exactly healthy vegetation, and the yellowness is using for the dry vegetation direction. Like the vegetations are dry, and there is a non-such case which is residual variance. So these are fixed base, and it is easier to interpret. But the interpretation or the PCA is adaptive, then it is optimal for the specific images. So that's a little bit different. Nonlinear transforms. So far we discussed the linear transform. Now it's starting nonlinear transforms. In the nonlinear transforms, you use nonlinear relationship between the bands. So far we have seen we were using the max bands as a weights in the linear transforms, but in the nonlinear uses non-linear relationship between the bands. Some of the common examples are vegetation index, water index, buildup area index, and the band ratios. So these transforms are useful because different land cover type has a characteristic spectral behavior. The nonlinear transformation is really important because the different land covers have a different characteristic spectral behavior. So due to this one, we are looking into the multiple indexes and its band ratios to find such kind of indexes. The first one is vegetation index. Vegetation indexes are based on a spectral behaviors of a green vegetation. So green vegetation are absorbed strongly in blue and the red bands. We already know about this since the first lecture. We discussed again and again. Reflects strongly in near infrared because of the leaf structure, and red band is often used instead of blue. And why, if we see to the sky, we already discussed this because as the electromagnetic wave passes from the atmosphere, so the blue band is scattered, and that's why the sky is blue. And scatter, which kind of relay scattering? Relay scattering is the reasons why the sky is blue. So it is short wavelength, and that's why it is scattered, and it cannot be passed from the atmosphere. So red band is often used instead of a blue because blue can be affected by the atmospheric scattering. And it is already affected, and that's why we don't have any blue. And that's why the sky is blue, and it is scattered across the whole sky. So simple vegetation ratio is RVI, means so ratio of vegetation index, near infrared divided by the red band. So the highly RVI usually indicates highly vegetation, or simply you can say vegetation. Now we have one of the famous ones. We passed one NDVI. NDVI is again a vegetation index, and its meaning is normalized difference vegetation index. It is the most widely used vegetation index instead of RVI. It is used differences between the near infrared and the red reflectors are almost the same. In the previous we have seen near infrared was divided by the red infrared red band channel. So conceptually, vegetation reflects strongly in near infrared because of the leaf structure, and vegetation absorbs the red light, as you already know about. Also, there is, especially in the vegetations, you are also absorbing the blue. That's why it is exactly the more green. So high NDVI indicates healthy vegetation. This is really important feature in a short comparison of RVI and NDVI. In this case, the high NDVI indicates the healthy vegetation. There is more features about the properties of the land types or covers. NDVI values are theoretically range from -1 to +1, like the standardized of the covariance matrix or the GLCM we have seen in the basic analysis. So typical interpretation is the below zero is exactly all the time water because they are absorbing the blue and red band both, and they are looking dark, and that's why it is below the zero. So because we know that the electromagnetic wave can be passes from the water. So if it passes far, dissolving, so bounce back is rare. So there is a chances that it can be darker. So it's easy, and also it can be shown by clouds, snows, or non-vegetation areas around the zero. Around the zero means like 0.002 or something like this kind of values. So they are the bare soil or build-up areas and weak vegetation, we can call them. So if it is above the zero, I mean like above the zero, we are crossing them, so vegetation is present. So 0.1 you can consider it is above the zero, it is a vegetation is present. And around the zero means near to the zero, 0.025, as I said an example. This is exactly how NDVI is represented and how they are classifying the different like covers types of the NDVI index in real time. And the 0.5 to 0.8 is a dense and it's a healthy vegetation. This is how we know this is healthy. Core idea, healthy in terms of very bright, very green. Core idea, NDVI highlights vegetation by contrasting high NIR reflectance with low red reflectance. So how we would know about the NDVI highlights the vegetation by contrasting of the NIR reflectance with low red reflectance. This is how we are looking into the or highlighting the vegetation by the uh, near infrared reflectance with low red reflectance. As you already discussed this in the topic, it's use the differences between the near infrared and the red reflectance. But in the RVI, if we see it is near infrared dividing by the red. So there is a minor difference. So the core idea is in the NDVI, the NDVI highlights the vegetation by contrasting the near infrared reflectance with the low red reflectance. If we see some of these images are reflecting like this is, we are going the red band is often used instead of the blue band. It can be affected by atmospheric scattering. So red band is already here used in the blue bands and red bands are absorbed strongly. So only green is remaining, so reflects strongly the green vegetation of the near infrared. So this is the simple vegetation ratio or VID equals to ratio vegetation index near infrared divided by the rate. This is exactly a very simple vegetation, and this is NDVI. We are only contrasting the near infrared reflectance with the low red reflectance. This is the second last index we are discussing. It is NDVI. It is a normalized difference build-up area index, and it's designed to highlight the area which are under the construction for urban areas. It is using shortwave infrared in near infrared both, but mostly shortwave infrared. Urban in build-up surfaces often shows a stronger shortwave infrared response compared with the vegetation. The response, the reason is exactly the same because the urban areas are not having any greenery or something like that. So the shortwave response compared with the vegetation is showing stronger instead of the near infrared. So typical interpretation is the NDVI less than zero means water bodies because the blue bands and red bands are absorbed very well and even the green bands is not passing properly. So that's why it's looking more uh, dark. The water bodies or non-build up surfaces. So as this is the build-up service, when it cannot represent the build-up services, non-build-up service surfaces, or it's either the water bodies. Between these two, it can be one, but there's a high chances of the water bodies instead of non-build-up surfaces. It is obvious if it is not a build-up service, so it can be a different thing. So most probably it is a water because it's all time less than zero. So the high positive in dBi build-up areas in the vegetation is usually high, has a low in dBi. And the reason because here is we are using the short wave response. The short wave response in the in dBi area is definitely low. So the core idea is the NDBI helps detect the urban or the built-up surfaces, especially at the low spatial resolution. When we are low in terms of the spatial resolution, then NDBI is really helping. So that's the nonlinearity using the indexes, so or the other bands reflectance to find the information. This is really helpful. As we have seen, the vegetation is usually has a low NDVI. Definitely here is we are dealing with the build-up area index, so it will be definitely low. As we have seen in the urban, in the build-up surface often shows stronger shortwave infrared. So the shortwave infrared is looking into more in the build-up areas in non-vegetated area. So that's the reason it's low in weak. This is the last one, MNDVI. MNDVI is the modified normalized water index. It is designed to identify in-map water bodies such as rivers, reservoirs, seas, and lakes. So it is uses the green in shortwave infrared bands. So the green band is coming from the visible, and a shortwave infrared is from the near infrared. So both of them are used by the MNWI. The water usually reflects more in green and absorbs strongly in shortwave infrared. So MNDVI helps make water bodies stand out. Stand out means black or dark. So if you see the statement again, the water usually reflects more in green. And the reason is it absorbs strongly in shortwave infrared. So the main objective of the MNDVI is to make help to identify or separate out the water bodies. For Sentinel-2, the shortwave infrared band of 11 is commonly used for the water bodies detection. So MNDVI enhance often open water features in unsupervised buildup our vegetation confusion better than the simple visual inspection. It is exactly the reason why we are using the shortwave in the green, shortwave infrared in the green bands. In the Sentinel-2, it is in a complete band for them to be commonly used for the shortwave infrared. But here, if you see, this is enhancing open water features in suppresses buildup or vegetation confusion. So this is really better in understanding the or no confusion between the buildup or the vegetation in the simple visual inspection. So in the visual inspection, there is a chances of a confusions with the buildup areas and vegetation or overlapping, but using MNDVI, shortwave infrared and the green bands, it is really helpful. Like as I said, for the Sentinel-2, the band number 11 is the shortwave infrared. It's commonly used for the water bodies detection. This is the last slide. We have almost reached the final of this lecture of spectral transforms. In summary, we have seen what is the spectral vector space and what is the spectral transforms, and then we have seen the two types of spectral transform, linear and non-linear. In the linear, we have discussed principal component analysis or PCT, principal component transform in more details, as we have already seen. And then we discussed tussle cape in the both of them comparison. Then we have seen some of the nonlinear spectral transforms of indexes like in DBV, in DVI, WI, and like modified normalized differences water index, in DVI normalized difference build-up area index, in DVI or RBI. So ratio vegetation index and normalized difference vegetation index. So these are some of the concepts we are usually discussing as the spectral transform. The last lecture will be about the land cover classification, but along the land cover classification, we will be almost at the end of the course, and that will be the last lecture of the glance also. And this class was about the advanced analysis in the advanced analysis in its application. So in the next lecture, we'll see you in about the land cover classification. For now, it's bye.